Hi, I'll be presenting DEALIO data-efficient adversarial learning for imitation from observation. This work is done in the Learning Agent Research Group at the University of Texas at Austin in collaboration with Garrett Warnell and Peter Stone. First, talking about the motivation. Adversarial imitation learning from observation methods have shown state-of-the-art performance in imitation from observation problems. However, these methods often suffer from high sample complexity, which makes them impractical to deploy in real-world settings. In this work, our goal is to bring down the sample complexity of adversarial imitation from observation algorithms to make them suitable for real-world applications. Before talking about the algorithm, I'll first give some background which is needed to understand the rest of this presentation. First, reinforcement learning. The goal of reinforcement learning is to make decisions by minimizing the cumulative cost feedback. As shown in this figure, for example, the agent is at state ST and takes action AT in the environment and goes to the next state ST plus 1. And during this process, it receives a cost feedback CT plus 1. And the goal is for the agent to learn a policy pi, which is mapping from states to the actions, by minimizing the cumulative cost feedback. Another framework that I'm going to talk about is imitation learning. The goal of imitation learning is to learn how to make decisions by trying to imitate another agent. In this framework, instead of the cost feedback, the agent is provided with some expert demonstrations, which include state and actions of the expert. And the goal is to learn a policy that maps the states to the actions. An example of imitation learning is this work of Scott Nickham, in which the task is to teach a robot to draw a cross on a whiteboard. To do so, the arm of the robot is moved around to show how the task should be executed. As it can be seen here, the agent has access to both states and actions of the demonstrator. Here, the states are the joint values of the robot, and the actions are the torques of the joints. One limitation of this framework is that the requirement of having access to the actions of the demonstrator precludes using a large amount of demonstration data where action sequences are not given. Okay, to alleviate the issue that I just mentioned, imitation learning from observation is introduced. Here you can see a video of imitation from observation in nature. The goal of this framework is to learn how to perform a task given a state-only demonstrations. In this framework, instead of demonstrated state action pairs, the agent is provided only with the states of the expert. And the same as before, the goal is to learn a policy that maps states to the actions. So now back to the proposed algorithm. In this paper, we propose a new algorithm, data-efficient adversarial learning for imitation from observation, DEALIO, to address the sample inefficiency in adversarial imitation from observation algorithms by integrating ideas from model-based reinforcement learning algorithms. We do this by integrating sample-efficient reinforcement learning updates from PILQR with high-performing GAIFO algorithm for imitation from observation. GAIFO is the generative adversarial imitation from observation algorithm. The resulting algorithm, DEALIO, is able to learn a time-varying linear Gaussian controller that can imitate a demonstrator using state-only demonstrations of a behavior. First, I'm going to give some background on PILQR. PILQR is an algorithm that itself is a combination of ILQR and path integral policy improvement. ILQR is a model-based algorithm and PI squared is a model-free algorithm. ILQR has some constraints. It requires the dynamics to be linear or close to linear so that the linear approximation would be close to the actual dynamics, and it requires the cost function to be quadratic. PILQR removes the quadratic cost requirement of ILQR. Instead, it requires only that the cost function to be twice differentiable. PILQR forms a quadratic approximation of the cost and makes policy updates by first using the ILQR approach over that quadratic approximation, and then performs a subsequent policy update using PI squared on the residual cost. At the end, it returns a Gaussian controller P of A given S. Now, I briefly talk about generative adversarial imitation from observation, GIFO. The algorithm works as following. First, initialize a policy pi in green, shown in the figure, and the discriminator D in yellow, shown in the figure. Then execute pi in the environment and store the state transitions. And then feed the state transitions of both the imitator and the demonstrator to the discriminator and train the discriminator with this provided loss here. And then use the discriminator as the cost function and train the policy using reinforcement learning algorithms like trust region policy optimization. And the process is repeated until the performance of pi converges. As discussed in the previous slide, the discriminator is used as a cost function to train the policy with TRPO or PPO, proximal policy optimization. Now in DEALIO, to lower the sample complexity, we use PILQR instead of PPO, and therefore the discriminator in its current format can't be used as the cost function since PILQR enforces some constraints. One constraint is that the cost function needs to be twice differentiable, and the other is to be a function of both states and actions. The function that we consider for DEALIO that meets these two constraints look like this. And as it can be seen here, the quadratic approximation of this function is the first two terms of it. Okay, now the goal is to change GIFO in a way to get the cost function in the blue box instead of a neural network. Again, a GIFO looks like this. Now instead of getting one value from the network, shown with V here, we get the elements of a matrix, a vector, and a number CC. Then we put them in this equation that is considered to be the discriminator for DEALIO. And so it returns a value, and similar to GIFO, the discriminator is trained to discriminate between the values that come from the demonstrator and the imitator. Based on GIFO, the output of the discriminator can be used as the cost, and the discriminator can be considered as the cost function. However, the cost for the cost function to be useful for training with PILQR, we need the cost function to be in the format of the equation shown in the blue box. And the first thing to note is that the function in the blue box is a function of ST and AT, but the current format is a function of ST and ST plus 1. And to change that, we use the dynamics model. As mentioned in the previous slides, in the process of PILQR, the agent learns a linear dynamics model of the environment, which we aim to use here. This model is used to substitute state ST plus 1 in the discriminator formulation with ST and AT, which results in the following equation that is only a function of ST and AT, and the matrix and the vector can be calculated using linear algebra. At last, the only difference that is left is that in the current format, the matrix, the vector, and the constant are all functions of ST and ST plus 1. However, they should be functions of time as shown in the blue box. And therefore, we take the mean of their elements over ST and ST plus 1 at each time to calculate them. Here, I'm going to present the overall sketch of the algorithm. First, the agent has access to state-only demonstrations and initializes a linear Gaussian controller, P of A given S. Then it executes that controller in the environment and collects samples. Next, it fits a linear Gaussian dynamics model, P of S prime given S and A, to the collected samples. Then the sampled state transitions and the demonstrated ones are used to update the discriminator introduced in the previous slide. Then the cost function shown in the blue box is extracted using the discriminator and the linear Gaussian dynamics model. And finally, the cost is used to update the linear Gaussian controller P of A given S. And the process is then repeated until convergence. Now the experiments that are used to evaluate DEALIO. The domains that are considered are these Mujoko simulation domains: disk, peg insertion, gripper pusher, and door opening. And we hypothesized that DEALIO is able to learn tasks efficiently and perform better compared to GAIFO. Our experiments proved that our hypothesis is correct. Here you can see the results of the learning process. Y-axis shows the performance that is normalized, and the x-axis shows the number of sample trajectories. We can clearly see that DEALIO has much better sample efficiency and it reaches to a better performance. Now I'm going to show a video of the performance of peg insertion. The first one is the expert video. As you can see, the arm moves the peg and inserts it into the hole. In this video, you can see GAIFO's performance after training. As you can see, it is not able to put the peg into the hole. And here is DEALIO's performance, which is able to successfully execute the task. Okay, so to sum up, we proposed an algorithm called DEALIO that integrates a model-based reinforcement learning algorithm to an adversarial imitation from observation in order to lower the sample complexity of adversarial imitation from observation algorithms and improve the performance of those algorithms. And also, I would like to thank my collaborators again, Garrett Wallner and Peter Stone, and thank you for watching my presentation.